This presentation discusses confidence interval for the population proportion. The notation is P. Now recall that the estimator for the population proportion is the sample proportion P hat, and P hat is the number of successes in a Bernoulli process divided by the number of trials. So remember, number of successes comes from an experiment of success or failure. Say for example you're interested in observing the number of defective widgets from an assembly line, and you could take a random sample of say 100 widgets, and so your sample size n, or number of trials, would be 100, and then discovering that 10 of those are defective, your p hat, which is the proportion, would be 10 out of 100. So 10 would be the number of successes in this case, and n, the sample size, would give you 0.10. Now interestingly, a couple of things. One, while x, the number of successes, is a discrete random variable because you can only have countable observations in whole numbers such as 1 defective widgets, 10 defective widgets, etc. P hat, which is the proportion of defective widgets in this example, is actually a continuous variable in a way, in the sense that proportions can take on any values. Now though, the distribution of p hat typically follows the distribution of x, which is binomial. But for large samples, p hat has approximately a normal distribution, and that's by appeal to the central limit theorem. And that's what we're going to employ in confidence interval estimation. Keep in mind that the mean of p hat is the population mean p. Now the population mean is the population the mean of p hat is the population proportion. I beg your pardon. The variance of p hat is the ratio of pq and n. Alright, that's pq over n. And the standard error of p hat, which is in essence the standard deviation of p hat, is the square root of pq divided by n. However, when we do not know p, when p is unknown, which is the population proportion, we use p hat to estimate the standard error of p hat. So in essence, the standard error of p hat becomes the square root of p hat q hat over n. And this makes sense because obviously if we're seeking to compute estimates of the population proportion, we don't know it, and so we really can't be thinking about using p and q to calculate the standard error of p hat. And so the use of p hat q hat instead of p and q is for estimation convenience. Now in general, here's a rule of thumb. If n times p and n times q are both greater than 5, we may already assume large samples and go ahead and use the normal distribution. But again, this is a rule of thumb, and you may use your discretion in the real world. Now then, what we can say is that for sufficiently large samples, the confidence interval estimation of p is shown here. It is equal to p hat plus or minus the standard error. The margin of error. The margin of error is the standard deviate z multiplied by the standard error of p hat, which is, which we explained before. So the product of these two quantities gives us the margin of error, which subtracted from p hat gives us the lower limit, and added to p hat gives us the upper limit of the confidence interval. And here's an example. A marketing research firm wants to estimate the share that foreign auto manufacturers have in the US SUV market. So to test that, a random sample of 100 US consumers is obtained, and it is found that 34 of these individuals own foreign-made SUVs. Give a 95% confidence interval for the share of US SUV market controlled by foreign firms. And so here note that p hat, which is the number of successes divided by n, is 0.34. So 34 out of 100 is 0.34. And so to calculate the limits, first we define the formula and we substitute in the values, and we find that the standard error is 0.0474, and multiplied by the z value of 1.96 for 95% confidence, we find a margin of error of 0.0928. So p hat minus the margin of error gives us the lower limit. P hat plus the margin of error gives us the upper limit. And so the margin of error is this distance that you see here between the lower limit and the mean value, and similarly between the mean value and the upper limits, keeping in mind that here mu actually is more appropriately shown to be p, which is the population proportion. And so we can also use Excel to obtain the limits of the interval. So let's go ahead and do that. Let's go here. Here we show our formula here to kind of guide us. We're testing at 95% confidence. For p hat in this problem, we have 0.34. So we type in 0.34. And for q hat, it would be, I'm going to use equal 1 minus p hat. That way I would never have to change q hat. Whatever p hat becomes, q hat will calculate correctly. If p hat is 0.2, and p hat calculates correctly, I should say. Alright, undo. And the sample size is 100. So we type in 100 there. And now Excel requires that we simply show the square root of p hat q hat and not the entire standard error. So that needs to be noted. So I'm going to hit equal, and then I'm going to use the square root function, open parenthesis. Alright, and it's going to be p hat multiplied by q hat, close parenthesis. And that's it here. You can expand the decimals if you wish. Now, expanding decimals does not affect your answers. It simply makes you see a little bit better what you have calculated. Your final result would still be intact because the spreadsheet stores all the values. And so for the margin of error, that's where Excel provides us with a function which is shown here. So the function is equal, then it's confidence, open parenthesis. It prompts us for alpha. So for alpha, you click here, comma. The next is standard deviation. However, this is a little misleading. What's required here is this, the square root of p hat q hat. So, and that's why I pre-calculated that, knowing what Excel is going to ask me. So I click on that, and then I hit comma, and then finally n, which is the sample size. I click on that, and then I close parenthesis and hit enter. And that is really the margin of error. So what we have here is actually z multiplied by this quantity, which is the standard error. So Excel factors that in when we type in n. And so the lower limit would be equal p hat minus the margin of error, while the upper limit would be equal p hat plus the margin of error. Alright, and if you're interested, the interval between those two would be equal the upper limit minus the lower limit. So we believe that within this interval, you can increase the decimals a little bit, that between these two limits, over this interval lies the true population proportion. How confident are you? You are 95% confident. Suppose you wish to be 99% confident, then type in 0.99 there, and automatically your alpha becomes 0.01. And as you can see, your interval expands, this time between 21.8% and 46.2%, providing us with this wider interval here. And if you wish to be 90% confident, type in 0.9 right there, and that recalculates, giving you a smaller interval, since your confidence level is a little less for the same number of observations. So going back to our presentation, we can also use the website prepared, shown right here, right, prepared by David Malone, and put in the values. So now here in this website, we're going to be careful to identify the mean to be the population proportion of 34%. The standard error is standard deviation is going to be truly the standard error, which is 0.0474. And then the shaded region would be the combined tail region. So let's go there. All right, and right there, let's see, let's get it right there. So we're not gonna use this first one here. This is not what we want. We need to scroll down and use the second argument. This is for 95% for confidence interval. All right, whatever confidence level that you wish to use. So here, excuse me, the mean again is 0.34, so we type in 0.34. And the standard error, standard deviation, as shown here, is 0.0474. So let's go there, all right, 0.0474. Now sometimes you might want to be, when you try typing in numbers in decimals, you might get an error message telling you that you have to type in real numbers, as if you weren't doing that before. So when that happens, play a little trick on this website. Start typing in regular numbers like 474, and then after you've typed it in, go ahead and go inside and adjust it like so, you know, by typing point and 0 in front of it. And if you wish to put a 0 in front too, that's fine, it's so far as you have your decimals placed right. And so your shaded region, which would be the combined tail region being 0.05, we click outside, and there you have it. 0.2471 is the lower limit, and 0.4329 is the upper limit, which is what is correctly shown here. By the way, alternatively, you could choose to identify the 95% confidence level, 0.95, but then you'd have to choose the area between, all right, so that it gives you this central region. Nevertheless, the limits would still be the same right there, which would be 0.2471, and over here would be 0.4329. So if you want the central shaded region of 95% used, then choose between, so it can correctly give you the limits. But if you want the tail regions to be used, in which case this is 0.05, choose outside, so it can give you the tail region outside of the limits on both ends. And yet these 2 points would be correctly shown to be, in this example, 0.2471 and 0.4329. Going back to our presentation, that concludes it. So the next section is confidence interval estimation for the population variance.